Should be good.
You are
Everybody's
good to go.
wonderful. Thank you. Well, thanks everybody. It is 9 o'clock in the evening here in the eastern part of the US. I think I'm covering many time zones this evening, so looking forward to this presentation and the ability to speak with everybody about the battery backup considerations for 5G RAN systems. And I'm the Director of Business Development at Inventus Power and the OCP primary contact, and work with our team of engineers, and essentially taking this information from a wide variety of customer applications, industry discussions, some research that I've done from some of the different entities' websites, and just trying to figure out what is really the optimal solution for backup in this new 5G world. And what I will tell you is that there's no concrete answer yet. We are definitely still figuring it out, but I'm going to share with you some ideas and concepts of what we're seeing and some of the trends and how we're going to try to make this reasonably cost and scalable and durable. So when we think about BBU considerations for 5G RAN systems, we all know that they are being deployed at a rapid pace. And there's a lot of new system architectures that are being considered between the different telecom providers and different end users. And I think if it was something where it was more just based on the mobile networks with the cell towers and the 4G style, that's one thing. But I think all of us are really trying to get our heads around what does this 5G system look like? And where are all the nodes going to be? And with the fact that we're going into these decentralized networks, and we're going into factories and on campuses and in hospitals, and we're working in remote industrial and agricultural areas, as our team just presented to us prior. There's definitely a significant power challenge for the network providers. And that's really what we're getting at with battery backup, is understanding what are the demands of the system, what are the risks of the power that's available to drive that system, and what are we doing essentially as the insurance policy. And that's where some of you guys have heard me joke around about it, saying that my product is the insurance policy that nobody really wants to pay for, but when you need it, you're really happy that you have it. So we're really kind of looking at this 5G as kind of the wild, wild west. So we see office building applications with micro data centers. We see applications out on street lamps, remote telecom cabinets, stadium applications. And my company actually does a lot of work in the geophysical space. So it could be mining applications, it could be hazardous applications such as fire solutions, and also agricultural applications. We're actually working on projects now that are supporting the latest in weather tracking or weather reporting type of information that are floating on top of the ocean, some that go in the bottom of the ocean. So that's kind of where we're seeing 5G as having applications just about anywhere. So really, what does that mean when we come up with this battery backup solution? It means that we need higher energy density, we need lighter weight, and that product has to be able to work in a wider range of environmental capacities. So the other piece of it is the further out into the edge, the more remote you make it, also puts a demand on the product to have a minimal amount of maintenance required. And with that maintenance in the network, what's really key is to offer that remote communication to let the system know, well, what's going on with the battery and how long has it been out there? And does it still have a usable life? Has it been put into work a little bit heavier than was expected? And the ability to send that information out into the network so that you can do either preventative maintenance or at least know that you don't have to touch it is really kind of key. The other piece of it is with the inconsistent power that's available to drive some of these 5G systems, the BBU is going to be asked to support extended runtimes. So as opposed to, say, a hyperscale data center application where 5 minutes is usually sufficient to cover everything needed to allow that system to do a graceful shutdown, in these instances, 5 minutes may not be nearly enough. So we're being asked to come up with solutions that can do 30 minutes, 45 minutes, an hour, scale out to run 4 hours, 5 hours, 6 hours. So in these applications, you can't assume that there's a backup generator that is available. This may be the backup generator. And in a lot of these applications, lithium-ion based solution is the optimal answer. We've heard more people saying, yeah, I'm not even considering sealed lead acid, it just won't work. We're going right to lithium in this design. So let's get into it in a little bit more detail. So when we end up having a conversation with the customer, we really have to go through a lot of different pieces to understand what is this going to look like. It's not like, you go to the store and you buy a AA or a AAA, you plug it in and you're good to go. We have to understand things such as the overall design parameters. What are the power levels? Where is this going to be located? And how long do you need it to last without anybody being able to access it? As you can see, we're on top of a building in this particular instance. And a service call to get up there might be pretty costly and challenging for the network providers. The other piece, as I've already noted, is scalability and system integration. We want to be able to have a battery unit that is modular so that the customer can configure it based on the different power levels that are needed in that particular installation. And there needs to be scalability because maybe they start with an installation with a certain amount of power, but they're adding to it because there's a population increase. And we need to be able to add more modules to support a larger runtime. The other piece is the interconnect, that when we have disaggregate systems out there, we need to make sure that we pick the right connector. And we'll go into that in a little bit more detail. And as I've already noted, the communication. The other big picture that we'll dig into a little bit further is the safety considerations and the agency testing. Pretty much everybody out there knows that lithium-ion has a reputation as being a fabulous product that works really well, high energy density, but everybody also has a story about thermal events. And what's happened is that the safety organizations have come up with new certification requirements that we'll go through again in a little bit more detail that really goes to the safety of some of these larger, higher powered battery packs. So going back to the overall design parameters, we talked about power levels, and primarily what we're seeing in the telco space is the 48 volt systems, but at the same time, you may have cabinets out there that have 12 volt datacom. So right away, I have two different power levels that have to be addressed depending on the system and the solution out in the field. And then we also have ranges anywhere from some very small systems of 200 watts and other ones where we're being asked to look at 2.5 to 3 kilowatts per module. And oh, by the way, it has to stay within 50 pounds. And we need to have this very long runtime. So right away, what we're being asked is to pack as much possible energy in as small and light of a space as possible. And that's pretty consistent across the board. But then it's also the environmental to say, well, we only want to have one unit out there that's going to be able to support pretty much everywhere we're going to be able to put this product. So we need to be able to run from -30C to 65C, which basically calls out for us to have heaters in the units and specific cells, and maybe even to an extreme, special chemistries on the cells to be able to support that wide temperature. And then of course, we need it to be waterproof and support the ability to run in 100% humidity, and then earthquake, lightning proof, high altitudes. I mean, all the things that you guys are pretty much used to. And for most electronics, it's not such a challenge to achieve that. But when we start putting cells and liquid and chemistry up into these environments, we have to do a lot of work within the physical packaging and the selection of the cells to be able to support these demands. And oh, by the way, we need to have this thing run for 5 to 10 years in the field without any maintenance. So what we also have to understand is how do those cells degrade in the product over time, and what do we need that runtime to be at the reasonable end of life? And by the way, can we send a signal out to the network operator to let them know, well, we're getting to this end of life, so let's plan a replacement. The other side of it is that if we have unreliable grid power, we may have a differential in the cell that we choose, because we might go to a lithium iron phosphate, which ordinarily gives us from 2,000 to 4,000 charge-discharge cycles. That doesn't give as much energy density, but if we know that it's going into, say, one of those countries or areas that does not have consistent grid power, this is something that you probably want to consider. So I hinted earlier at the modularity and scalability, and really what that comes down to is how do you build out a particular system that it's easy to add modules as needed. And one of these is also where people are kind of used to saying, well, if say one battery is 500 watts and another one is 2.5 kilowatts, well, they can be different physical sizes and different packaging. Well, actually, kind of what we're looking at is it kind of makes sense when we think about the costing of the unit and the development costs, which are actually pretty significant, to actually keep the product in the same voltage and in the same possible box or housing, and use the same interconnect, and then just essentially scale up or down the number of cells inside of that box. Because what that does, it gives us a little bit of ability to certify families together, and then also get an economy of scale. So one of the things I know guys on my team tease me about is the interconnect, because I also spent a lot of years in the interconnect space. And it's a small item on the physical product, and it's not really a high cost piece of it, but it's a really critical part of the overall pack design. So we have to have the right IP rating, and we like the idea of having field termination on the product so that depending on where the installation is, it's really easy, and you don't have to actually access the internals of the battery itself. So it is something that's really important to consider in the design. And also, if you can do something where you have power plus signal in the same connection, because we're also incorporating signal between the different packs and the different PDUs that are part of the system. And it's again something where the installer is going to look for, well, what's easy to get to, that I can strip and terminate easily to work with. And then also, if you damage a connector on that product, it could be a $700 battery that you're saying, well, now it's damaged and it has to go back for repair. So, kind of one of those small areas, but again, it's all the attention to detail. And as I mentioned, communication, we recommend RS-45, CAN bus. I mean, there's a couple of other communication systems available. And you're able to then access the state of health, state of charge, event details in the system. So going over to those safety considerations, as I mentioned, UL 1973 and IEC 62619 are the major ones that have come online over the last 2 or 3 years. And both of them really make it imperative to essentially mitigate a single cell failure from becoming a catastrophic event, to keep that failure from propagating to any of the adjacent cells. So we have to actually do work on the internals. We increase the gaps between the cells. We have to have venting mechanisms. We sometimes have to add extra materials on the inside of the pack. So it does go away a little bit from the density requirement, but on the other hand, you also don't want to have a 2.5 kilowatt hour battery pack out there that has a thermal event. So really kind of important. But as I mentioned earlier as well, the testing is very expensive, from 75K to 125K for each one of those tests. Actually, that would be a combined. So, if you have a different power level, but it's the same voltage, it's another test. So each configuration that you do, it has that $100,000 test to it. And then on top of it, we have all the Bellcore, all the NEBs, all the other testing to do. So, you're looking at anywhere between $500,000 and $1 million of development cost on a product like this. So let me show you a couple of examples as I get wrapped up here. As I mentioned, a lot of modularity. So here's an outdoor backup solution for 5G. It's a 48-volt regulated or unregulated output. We can either use lithium iron phosphate, lithium ion. As I mentioned, various power ranges. They're hot swappable, parallel connectable, different communication protocols, and are designed to achieve the UL 1973 and IEC 62619. Here's another one, a little bit smaller, a little bit more slimline, same general idea, but kind of designed for some of the smaller power levels, say from 500 to 1.5 kilowatts. And as you can see on here, those yellow portions, those are heaters. So, this product's designed to be used in a low temperature environment. And as I mentioned earlier, OSHA requirements of less than 50 pounds. So that's always going to be baked into the design as well. And then, as many of you have seen, our solution for really the data side of the equation, the airframe or open edge solution. So we do have a proposal out there for a 12-volt, 1600-watt sled to go into the 3U or the 2U high system. And then, of course, we also do cabinet level backup solutions, which we're being asked to take a look at as well. I would say this would get into a whole other presentation, whole other set of requirements, but it's an area that we're being asked to consider versus the sealed lead acid that is so prevalent out there in the telco field. Again, because of density and because of weight, that we're being asked to consider putting together some lithium ion or lithium iron phosphate solutions. And then just kind of some work that we're doing in the solar field, but this could be extremely valuable in a far edge agricultural or geophysical type of application where maybe power really just isn't available at all, to essentially have a solar panel that is designed to meet all the telco requirements as well. So to wrap up, I want to at least give some credit here to Ericsson, Nokia, CommScope for some of the information that they've made available. There are some links to go read up a little bit more about it. If you want to hear a little bit more about some of the different chemistries and the lithium ion industry in general, a link to a white paper that we publish each year. And yeah, I would basically ask you to share application information from your installations. People who have to get pretty creative. We'd like to hear what they see out there in the edge and far edge, and present some of these concepts as part of our Telco Edge project community. So thanks.
Thanks, Howie. I'm looking here and I do not see any comments yet. Does anyone else see any comments? Everyone else is talking on mute, so please unmute.
Well, that's because I didn't see any comments.
Okay.
They'd only be all my own, so I don't want to, hog up Howie, but lots of good stuff there. It's good content.